4.4 is on applications of integration, and we're going to be analyzing rate graphs. So just like we did with derivatives, after we talked about what they were, we analyzed how that applies to a graph of a rate. We're going to use this added knowledge about the relationship of integration and area under a curve to now look at rate graphs through a different lens. Something really important to keep in mind when you're looking at these rate graphs is to pay attention to the units on the x and y axis. And remember that if we're finding the area, we're multiplying those units together. So for example, if R of t was in feet per hour and t was in hours, we would be multiplying feet per hour by hours, and that product would give us feet. So really, when you're analyzing these rate graphs, you need to be paying attention to what's going on with the units. And really, all that we're going to do in this section of notes is analyze some rate graphs, look at different types of problems, and work through those practice problems. There's no big concepts, just how do we work through and use a rate graph. That's the big idea today. So this is one of those lessons where I actually recommend that before each problem, you pause, work through as much of that problem that you can, and then come back and watch me work through it and see how far you can get without me, which for most of you is probably pretty far. So, given the graph to the right, that it models rainfall in inches per hour from midnight to 6 a.m. during a storm. Number 1 says, write a sentence to explain what point A on the graph represents. Make sure to include numbers and units. So point A is right here. So the x-axis is talking about time after midnight. So x is 3. So that means we're talking about 3 a.m. The y-axis is talking about the rate of rainfall at that time. So at 3 a.m., the rate of rainfall is, what's that y value? 1 inch per hour. Number 2 says, what is the slope of the graph between points A and B? Well, that's an Algebra 1 question. If we look at the slope between points A and B, we can see that that slope is 0. Number 3 says, explain what that slope in number 2 means. Well, what that means is between those 2 points, between A and B, which is 3 a.m. and 4 a.m., there was no change in the rate of rainfall, which was still 1 inch per hour. So that doesn't mean there was no rainfall. It means there was no change in the rate. Number 4 asks, what is the slope of the graph between points B and C? Well, it's going down this far. This is actually just 1. All of this, and looking at the units over here, it's going down 1 and it's going to the right 1. So our slope is -1. Write a complete sentence saying what that means in context. So B is 4 hours after midnight. So between 4 a.m. and 5 a.m., the rainfall decreased at a rate of 1 inch per hour squared. So what we're doing is we're looking at the slope of the rate of change, which means we're looking at how the rate of change has changed. It's kind of a mouthful. So between 4 a.m. and 5 a.m., the rainfall decreased, since it's negative, is 1 inch per hour squared. Or you could say the rate of change of rainfall is -1 inches per hour squared. So again, here you can either say that it decreased at the rate of 1 inch per hour squared, or you could say that the rate of change of rainfall was -1 inch per hour squared. So just make sure you're not having a double negative situation. Number 6 says, find the integral from 3 to 5 of r of t dt, which is basically saying find the area of the shaded region. Area of the shaded region. Since it does not specifically tell you how to do that, and since we're not given a function, you can basically use any approximation that you would like, but I will point out this is just a trapezoid. We know how to find the area of the trapezoid, so this is not an estimate. So this integral is equal to the area under the curve, which is going to be 1/2 times the height, which is actually the y value. So the height is 1 times base 1 plus base 2. Well, base 1 is from 3 to 5, that's 2. Base 2 is from A to B, which is 1. So 1/2 times 1 times 3 is going to be 3/2 is the area under the curve. And we should probably make sure we include units here. So what did we just do? We multiplied inches per hour by hours. So that's going to give us 3/2 inches. Okay, I have to go to the next slide to continue with this problem. Number 7 says, write a complete sentence to explain the answer in number 6, so the area under the curve. So what this is saying is the total amount of rainfall between 3 a.m. and 5 a.m., that was the area under the curve, so the integral from 3 to 5. The total amount of rainfall between 3 a.m. and 5 a.m. was 1.5 inches. And then the last question relating to this specific rate graph says, approximate how much total rain fell from midnight until 5 a.m. So something to keep in mind, we just found the total rainfall from 3 to 5 a.m. So we could actually set this up as 2 integrals. We could look at the integral from 0 to 3 of RT dt plus the integral from 3 to 5 of R of t dt. And this we just said is 1.5. So to find the area from 0 to 3, what we're going to have to do is look back at that curve and estimate that total area. So let's go back a slide. We already found the area of this shaded region. And since we don't actually have a function to integrate, we're going to estimate this other area. So what I'm actually going to do is I'm going to break this remaining area into 2 pieces. You could do it in one, and actually I think you could probably, if you know what, I'm going to do it differently than I did before. I'm going to do this as a triangle. It's obviously going to be slightly less of an estimation, but I still think it's going to be a good estimation. So the area of that triangle is going to be 1/2 times the height, which is 1, times the base, which is 3. So 1/2, so I'm going to say approximately 1/2 times 1 times 3. So that's going to be 3/2 plus 1.5. That's going to be 3. And what are we talking about here unit-wise? We are talking about inches. So just to point out, what I just did was I estimated the area of a triangle. If you actually look at my worked out notes, I broke that integral up into 3 pieces, and I found the area of a trapezoid here and the area of a rectangle here, and I added that to the area of the other trapezoid. So as long as you are being clear about how you're estimating the area, there's a lot of different approaches to take, and all of those answers are going to get you to pretty similar places. So I think if you look at the worked out copy of my notes, I ended up with 33/10, which is pretty close to 3, a little bit more. So let's look at another example. All right. A cross-country runner is on a 20-minute practice run. The runner's velocity is shown in the table. We're going to do a lot of stuff involving this table. So one thing that I did to help myself while I was working through this problem is I actually created a graph of what's going on in this table. It just made it easier to visualize when I was approximating area how to break shapes up into smaller pieces. Now you definitely don't have to do that. If you're approximating, number 9 says approximate the total distance using your favorite approximation method, you could in theory just use a left-handed Riemann sum and use rectangles for each thing. So you have the base and the height in this table. You could break it up. That's probably not going to be the most accurate way, assuming that everything is a rectangle. You could break it up into smaller shapes. So as long as you're being consistent and clear with how you're finding the area, there's a lot of different correct answers that you're going to come across that would all be equally accepted. So there is the graph that I created in my notes. Again, you do not have to graph. You could use the table. On a lot of these problems, you will see people use the table, come up with an estimation based on a left or right Riemann sum, and that's something that you could stop by student support and we could go over if you are interested in seeing it that way. After I sketched this out, it seemed pretty clear that I was going to be using a triangle, so you can actually see the 5 different areas that I broke it up into. A triangle and then 4 different trapezoids. Something incredibly important to notice is that we're talking about minutes and we're talking about miles per hour, and those units are obviously not the same. So when I'm thinking through that, I need to either, you could in theory at the very beginning convert this entire table, have the time be in hours, or you could deal with it afterwards. So what I notice is that the width, because of the way I'm breaking up these shapes, the width, which is the issue that I had, the width is in minutes. The width for each of these shapes is 4. And if I convert that to hours, 4 over 60 is going to give me 1/15 is going to be the width that I'm going to use so that I have hours for both axes. So the width that I'm going to use for each shape, each of the 5 shapes, is going to be 1 over 15. So the distance, the total distance traveled, is going to be the areas 1, 2, 3, 4, and 5 added together. So let's look at those individual areas. So the area is going to be approximately, since this is not, I'm not using exact values, let's find the area of the triangle first. 1/2 times 1 over 15. And actually every single shape that I'm talking about, I'm going to have to do that, right? Area of a triangle and area of a trapezoid, we say 1/2 times the width, which is going to be 1 over 15. So I'm going to just put that in front. Area 1, base times height times 1/2. So the base is 8.8. So that's my area for area 1. Area 2, I'm going to have to add the 2 bases together since this is a trapezoid. That's going to be 8.8 plus 9.5. Area 3 is going to be 9.5 plus 9.7. Area 4, I'm going to move my picture. Area 4 is going to be 9.7 plus 9.3. And area 5 is going to be 9.3 plus 10. So if I add all of those values together and I multiply them by 1 over 30, I'm going to get that my area approximation is 2.82. And we're talking miles here because we multiplied miles per hour times hour. That's going to give us 2.82 miles. Number 10 is going to ask us to find the average speed. So I'm going to call that S average, which is going to be 1 over 20 minus, actually let's convert this, 1 over 20 over 60 minus 0 over 60, right? Normally I would just say 20 minus 0. However, I want these to be in consistent units. So 20 over 60 minus 0 over 60. So that whole thing is going to become what? 1 over 1/3. So that whole thing is going to become 3 times the value that we just found in number 9. So times 2.82. So this is going to become 3 times 2.82. 2.82. And that is going to give us 8.46 miles per hour. That is the average speed over this interval. Number 11 says, use the table to approximate the runner's acceleration at time t equals 10 and at time t equals 14. So this question is actually really an Algebra 1 question. It's asking you to approximate the slope given 2 points. So if we're looking at 10, which let's do 10 first, 10 is going to fall in between 12 and 8. So the best that we can do to approximate what's happening at 10 minutes is we can find the average of what's happening between 8 and 12. So f of 12 minus f of 8 over 12 minus 8. F of 12 is 9.7. F of 8 is 9.5. 12 minus 8 is 4. This is going to give us 0.05. And this is miles per hour. But miles per hour per minute, we want this to just be in terms of not minutes and hours. So let's use a conversion here. Let's multiply this by 60 minutes per hour. So that way the minutes units will cross off. 0.05 times 60. This is going to give us 3 miles per hour squared. We're going to do the same basic process for when t equals 14. So now we're going to be looking at So when t equals 14, we're going to be looking at what's happening with 12 and 16. So f of 16 minus f of 12 over 16 minus 12. This is going to be over 4. F of 16 is 9.3. F of 12 is 9.7. So when I subtract those, I get negative 0.4. I'm going to take this and I'm going to multiply this by 60 miles or 60 minutes in an hour. And that will give me negative 6 miles per hour squared. Miles per hour squared as our answer for what's going on when t equals 14. All right, number 12. What is the minimum number of times that this runner had a velocity of exactly 9.9 miles per hour? And between what two data points can we guarantee that velocity and why? So this question, without saying it, is asking you to use MVT. So looking at this problem, we know that this is continuous and differentiable. So we're going to mention that because we always do continuous and differentiable. Therefore, MVT applies. You could say MVT for integrals applies. If we look at the table, we're looking for any time where we're going from one number to another number and 9 would be between them. So that's happening right here. Between 4 and 8 minutes, we're going from an 8.8 average to a 9.5 average. Nowhere else are we crossing over the number 9 looking at our velocity. That means that between 4 and 8 minutes, the velocity must have been exactly 9 miles an hour at some time. So between 4 and 8 minutes, the velocity goes between 8.8 and 9.5. Therefore, it must have been 9 miles per hour during that interval. And that's true because of MVT. And then the last question relating to this problem says, can you guarantee that at some point during the run, the runner's acceleration was 0.5 miles per hour per minute? So what we need to do is we need to find the average acceleration first. So let's go ahead and do that. We're going to find the average acceleration on the interval from 0 to 20. So that's going to be f of 20 minus f of 0 over 20 minus 0, which is in fact going to be 1/2 miles per hour per minute. So since this is continuous and differentiable by MVT, yes, we can guarantee that. And that's going to wrap up this problem. There's one last problem, and I really encourage you to pause the video and work through it on your own. I will point out that this problem specifically has a little asterisk, which is my way of telling you you should be using a calculator to do this derivative and integration work that arises. A person is filling a bathtub in order to bathe and opens the faucet at 6 p.m. The rate at which the water is entering the tub is modeled by this function B of t, measured in gallons per minute. So question A asks how much water is in the tub at 6:05. So that means we're going to take the integral from 0 to 5 of B of t, and you're going to do that on a calculator. That's going to give you 27.793 gallons of water. Part B says, if the tub's fill line is at 50 gallons, will the bath be ready by 6:10? Explain why or why not. So let's look at the area under the curve from 0 to 10 of B of t dt. And again, you're going to plug this in on a calculator. This is going to give you 53.917. So the fill line is happening at 50. This is obviously greater than that. So this is also gallons of water. So yes, we can guarantee that because the total area is about 54 gallons at 6:10. The last part, part C, says when the bath is over and the plug is pulled, the amount of water remaining in the tub is modeled by this new function E of t. As the water empties, is the rate of change of the water emptying speeding up or slowing down? Describe how you know. So what you need to do is you need to graph E prime of t, because we're looking at the rate of change of the water emptying. So you need to look at the graph of E prime of t, and you need to figure out what's happening. So grab your graphing calculator, type your y1 is your E of t function, type y2 is the derivative of that y1 function, and then look at the graph. When you look at the graph, it's increasing if you're paying attention to that slope or what's happening with that graph. But if you actually hit second table and type in 1, 2, 3, 4, see what's happening to the y values when you do that with the x values. What's happening is that it's going from a more negative number to a less negative number. So what does that really mean? I'm starting at like negative something. I'm getting less and less and less negative as the time is increasing. So what that actually means is that the water is being emptied, so the speed is slowing down. Which is what that question was asking. So the big idea in 4.4 is about how to analyze a rate graph. Make sure that if you're being asked to approximate area, you're using any sort of Riemann sum or just using different shapes that you know how to find the area of. Pay close attention to units and make sure you're paying even closer attention to what each individual question is asking. Looking forward to doing some more practice on this in class. Thanks for listening.